Hello, my name is David. This is a mic test. I was streaming. Hello. Hello, this is David. This is a mic test. I hear myself. Right, is this thing working? Yes, sounds promising. Yeah, you can hear my voice. Nice. Okay, cool. Right, let's get this thing started. Right, hello, welcome to the DigitalOcean Amsterdam August edition. My name is David. I'm the guy in charge of all the beers. Yes, if you want more beers, talk to me. We also do non-beer options. Yes, this is the August edition of the Amsterdam DigitalOcean Amsterdam meetup. This is the office of Your Majesty Amsterdam, and you made it here successfully, so that's test number 1 complete. If this is your first DigitalOcean Amsterdam meetup, you are probably curious as to what a DigitalOcean Amsterdam meetup entails. We do this once a month. They tend to be on tech-related topics, although we do branch out occasionally and do weird and wonderful stuff, but mostly it's tech and the internet. Yeah, we get some great speakers in, and we have lots of beer, and there's non-beery options, and there's lots of freebies, which is great. And yeah, we just have a good time. It's pretty chilled. No corporate sponsorships. Well, other than DigitalOcean and a few others, but anyway, it's not big recruiter things. The agenda for tonight is doors are open. Yeah, that's good. This is the introduction to the meetup. Then we've got Ian. And these two people are going to give us a fine talk on machine learning with flash flooding. So I'm really excited because that branches 2 of my interests, like my geography degree and machine learning, which is a tech that I do for day jobs. That's great. Afterwards, we have a very exciting raffle for the O'Reilly Artificial Intelligence bronze pass, which is really cool. I also have machine learning books, because books are great. And we have t-shirts and stuff in there, so you really want to be in that. So I'm hoping you got a sticker, because that's how you enter. We have a code of conduct because yes, this lets everybody know how they should behave and what will happen if they don't. So yeah, DigitalOcean is dedicated to providing a harassment-free event experience for everyone, regardless of gender, gender identity, expression, age, sexual orientation, disability, physical appearance, body size, race, ethnicity, religion or that thereof, or technological choices. There is a lot longer version on the website. Like, this is just the little synopsis, but like basically treat everybody nicely and everyone has a great time, and then we're all good. Yeah, if there is an emergency, yeah, fire exit is like literally just behind you. Toilets are over there, by the way, as well, if there's that kind of emergency for you. Yeah, literally just over there, downstairs. And then we hang out in the rain. It's not raining. Great. On the bridge with a beer. If there are any, if you, I don't know, fall over and hurt yourself, this is yet to happen. So don't make it a first time. But if it does, we probably have some paracetamol and some bandages, and we can call ambulances. But like, we don't want that to happen. So, but it's there if you need it. Yes. This meetup would not be possible if it wasn't for a glorious load of sponsors. So I'll have to go through those. DigitalOcean obviously sponsors the event because it's kind of their meetup. If you don't know who DigitalOcean are, they do servers essentially, and they put a nice software on front of servers. This, in case you don't know, is what servers look like. Lots of cables and lights and big fans, and it makes a lot of noise. And this is what the DigitalOcean little UI looks like, and it's kind of nice. There's a nice UI. If you don't do code, you can just spin up an instance and you're ready to go. Or if you're really into it, there is a terminal commands, and that's great if you're super nerdy. So it's good for everyone. Ultimately, doing servers is quite hard. DigitalOcean make it slightly easier, so that is great. And these guys paid for. Well, we have a shed load of beers tonight. Half of them paid by Picnic, half of them paid by DigitalOcean. I think we have 16 crates of beers. So get drinking. But yes, they're super helpful. They paid for the pizza. That's the main important bit. This is Your Majesty office. We are a bunch of people. Here's most of us, plus wives, girlfriends, children. That's us, and we do website things for phones. This is the Universal Love Songs for MGM Resort. They remade classic songs for the LGBTQ community. So that was really cool, and it looks super nice, and it works on phones. We also do stuff for ski brands. This is Rockefeller, And we also do machine learning, believe it or not. This is predictive eye tracking using machine learning. This is an in-house startup we do, which is cool. I'm not going to take up too much of your time explaining all the things. O'Reilly, these guys gave us a free ticket to their conference, which is worth like €1,000. So that's kind of nice. They also give us books. So there's what books look in the internet, and then they look like in real life, which is super cool. So it's like exactly the same thing. So they give us books and swag. They're super amazing. There were tattoos over there. If you want a tattoo, I can find you one. Yes, that's super cool as well. Really love those guys. And they also do conferences too. If you don't win the raffle and you want to get discount off conferences, you can use this code, which is USRG. This guy taking a photo. Yep. And then also, I think this does the same thing, but like there are two codes. One of them will work, and well, hopefully both of them will work. But we will see. Yeah, they can both get you 20% off, so that's good. And they do really great conferences like Velocity and Artificial Intelligence Conference. So yeah, this one's in London. There it is. And we also have a bronze pass, as I mentioned previously. Picnic, these guys are sponsoring the drinks. They bought us, and they also gave us snacks too. They gave us another 8 crates, which I was not expecting. And when they turned up, yes, so they're all downstairs. So you guys keep drinking it, we'll keep supplying it. In case you don't know who Picnic are, they're kind of a bit like Albert Heijn, but they're like an online-only supermarket. They started 3 years ago in Amersfoort, and since then they've grown to like 60 locations across the Netherlands and Germany, and they now serve 100,000 households. So that's really good. They do free delivery, €25 instead of Albert Heijn 70, and they give you a 20-minute delivery window rather than like 2 hours. So they're pretty good, and they also do machine learning and really cool stuff like that. We've had a few of them in doing talks in the past, and they've been really interesting. So we're really grateful for their help, which is good. Yeah, the calendar. Yeah, next month we're going to do another how the internet works. Since I made this slide, we got contacted by a dude who is the Chief Technology Officer for the Internet Society. He's going to talk to us about DNS routing security. So that's going to be super nerdy, but hopefully really interesting. And then I'll get another speaker, and that'll be super cool. And then on the 2nd, which is super early, we normally do them at the end of the month, but yeah, we do this one is the Frontiers Conference pre-party, because they have a 2-day conference for front-end devs on the 3rd and 4th. And that means they have awesome speakers in town, so I have stolen them the night before, and yes, hopefully they will present to you guys. And then also we've got an ADE special, because yeah, I like ADE, and we can do music, cool things. So we've got like Internet of Drums, and I need to find another talk for that, but yeah, that's coming along. So that's what the next couple of months looks like. All of these people are not here. Hugo is ill, Erica is off gallivanting around Amsterdam with her family and relatives, and Valerie is busy doing stuff. So it is me, myself, and I doing tonight, which is why it's a little bit crazy. Thankfully, Eleanor volunteered to help sign you guys in, and she is a lifesaver because I cannot do all this on my own. But yes, I'm super grateful for that. Yes, if you have any feedback, you can either get me on Twitter. It's David Endersby1, because the original David Endersby was taken. And yeah, my SEO rating is so much better than his, so I'm good. And then Samantha C, she's also on Twitter, and I think I ruthlessly destroyed her name, but that's her on Twitter. She runs the DigitalOcean community internationally. So if you want to say nice things or horrible things about this meetup, you can send her messages. If you don't want to do them on Twitter, you can do them via email at samantha@digitalocean.com. And if you want to say anything, you can use the DO meetup hashtag, and I will try and scout the internet, hunting for those, and like it. That is all from me. I'm going to hand off to these two handsome chaps, and they are going to give us a talk on machine learning for flow planning. Cool. Right. Let's ship across. Who's going first? You're going first, so I'll give you that one. So that goes in your pocket. This goes around your neck. There we go, sit on that. And then you need to get your tool. So that goes in there. And then this is just a microphone for a live stream. So this. This. What's in there? I'm hoping. Searching. Promising. Good news. Yep. And start. Right, can we give them a nice warm round of applause? Thank you.
So, good evening, everybody. So, my name is Yuri. I'm also the co-founder. Happened. Anybody? Technical issues. David, you need to help us.
No signal.
It failed at the beginning.
This is the one problem, is the cables.
Okay. Cool. Okay, so I'm gonna stay here. So I'm also the co-founder of Transight. And recently we've been working with one of our customers doing some machine learning projects, which is about the urban flooding prediction. So this evening is the evening of machine learning, so we're going to talk about this. So the agenda, we're going to talk a little bit about what we do in Transight and the background and the problem of the project. Then Ian going to take over to tell you a big story he made for analytics. Then we're going to wrap it up and some Q&A afterwards. So first of all, what we do in Transight. So we are a data analytic company. Basically, like others, we help our customer to deliver cloud-based, data analytic solutions like ETL or data pipelines, data platforms, etc. So we will make sure it's production ready if it's needed. But if you are an enterprise customer and you're looking for some more scalable, secure, reliable solutions, we can also provide you with an enterprise level data platform based on Panda. So does anybody know what Panda is? Nobody? Okay. So this is an open sourced data platform initially designed and built by Cisco internally. So of course it's designed for network data analytics. It's Cisco, right? But they open sourced it and it's really powerful. And there's a lot of interfaces and plugins have been developed for this. So now it not only handles the network data, but also the streaming data or IoT data, etc. That's why it's very powerful. And the partner we are working with, they are the core developers in Cisco, actually built this, write the code for this. So we have a lot of advantages to deliver this service to our customer. And of course, we work closely with our customer to build machine learning models or data analytic solutions for them and applications as well. So this is a Transight in a nutshell. Every time I have to click twice. So I'm going to show you a video about urban flooding. So just in case some of you have never experienced this before. So this is going to give you a very nice picture how it looks like. Okay. So there are some sounds, but don't expect too much. Just know with problem. So this is in a city in China, in West East, and this is a subway. So after the storm, there's a lot of flooding on the streets. And this is in the northeast part of China. And guess this is Germany, in Berlin, also a subway station. I can't remember when, but this was happening. Also in Toronto, in Canada.
A wild night, an intense storm brought flash floods that left many waterlogged and stranded.
Yeah, he obviously didn't recognize what this over there. Another one. Yeah, it's actually just pretty dangerous.
The city affected. Not far from where we are, Catherine, there was a TTC streetcar that got stuck as it was passing through an underpass in this part of the city. And
Yeah, some funny stuff. Yeah, sometimes some fun with it. You cannot hear it, but I can hear people laughing. So, yeah. So this is about the problem, the urban flooding, what it is. So I just want to ask: is there anyone there have ever experienced the same thing in your life? Well, quite a few. Okay, yeah. So I had the same experience when I was like 8 or 9 years old. I think it's 1998 back in China. So there's a huge flood there in the south part where I come from. So it was quite a lot of fun for me. I mean, as an 8-year kid, you don't need to go to school and you can play with the water, right, in the summer. But actually, there's no fun at all. If you live there, you walk in the city, you probably lose your life because of this. So these problems exist not just in developing countries like I showed you in China, but also in developed countries like Germany or Canada, many others. And these will cause huge private and public property loss during the flood. You probably will lose your car or your house, and even worse, somebody lose their life during this flood situation. So what is the current solution that the government is doing to mitigate these kind of floods, disasters? You might be very familiar with this, right? This is a pump people use to pump out the water from a lower place to, for example, a river next to it. And okay, let's do this. And this is the sandbags, or or whatever materials that you use to cut off the water from your houses, for example. It's quite handy. And of course, you need a lot of people to execute this, especially in China. That's our advantage, human capital. So you use them to actually do the work. And this is actually a real picture. So these people are the People's Armed Police Force, the PAP in short, PAP force. So they become part of the army during the war, and while in peacetime, they are responsible for some emergency situations like the flooding or some terrorist attack if it happens. So I have a question for you guys. Do you see any commonality of all these? So what actually are all these kind of things? Can you use one word to describe it? Red. Yeah. Okay. So of course everybody has their own opinion. So I made the words. It make perfect sense. Of course in this presentation, they are all resources, right? So the pumps, the sandbags, or whatever the people, they're resources the government need to arrange and place in the right place at the right time to save lives. So how to manage these kind of resources wisely is very important, since this doesn't work anymore. So we're not that old-fashioned. It's not just human capitals. There's a lot of IoT solutions, sensors, 4G, these kind of things already deployed for many years in these areas. So there are over 150
What the heck?
Yeah, while you're fixing it. So there are over 150 sensors. The real-time flood level monitoring sensors looks like this in the city, spread in the city, and also they have a lot of rain gauge measurements in the weather station on top of the building. So they will measure the rainfall in real time. Okay. But these kind of devices, I mean all the technologies, they're still not enough to mitigate the damages that caused by the flood. The reason is urban flooding, it happens at extremely rapid speed. and concentrated both in time and space, which means it happens very quickly, and the flood come and do the damage. So even before you send the resources, you realize it. So the data that you collected from all these technologies, you can build very nice dashboard to show your boss, like, and get promoted probably, because a lot of big companies, they are doing this kind of thing which is called business intelligence, right? But it's not solving the problem. It displays the problem, but doesn't solve the problem. And the government there is still following these very reactive methods or solutions to mitigate these flooding problems. I'll try this. So the requirements we got from our customers is how to predict the flood severity 3 hours in advance. So why 3 hours? Of course, based on the data quality, the frequency we have. But on one hand, 3 hours is a comfortable time for the government to actually arrange the resources and deploy them into the right place. And from discovering the risk of the floods and to deploy the stuffs there. I don't exactly know if these 3 hours are really what they need, but a lot of political reasons, it's not just doing things, but there's a process there. So on the other hand, 3 hours. So what do you think, what do they really want? Do the government need the water or the flood level in 3 hours from now in the future? Or it's something different? So is there anybody can tell me what exactly this 3 hour in advance means? Maybe let me give you an example. So now it's around 7:30, let's say 7 something. So I tell you that by 10 o'clock, at 10 o'clock, there will be 50 centimeters water downstairs. It's raining, so possibly. And as a host, DigitalOcean, what are you gonna do to help us out? Because we want to go home.
We'll be okay up here. There's enough beer to keep us going.
Yeah, good one, good one.
Dehydrated.
Okay, good one. So imagine you are the decision makers, you are the police or the government. What are you gonna do with this kind of information I tell you? I predicted 3 hours in advance.
Tell the people.
Yeah, but okay, wait a second. So I just told you that there will be 50 centimeters water at 10 o'clock, 3 hours from now. But I didn't tell you actually when this 50 centimeters water actually happen. When? It probably happened in the first hour, 7 to 8. Probably happened in the second or the third hour. And probably in the second hour it's 100 centimeters and then it goes down, right? So this is a bit tricky. I'm gonna leave it and Ian's gonna tell you more about this. Just a second. Okay. No, finish. Just 2 more slides. So imagine that we're able to predict the flood 3 hours in advance. Then we should be able to have a more predictive, proactive solution for the urban flooding. And based on that, we should be able to, lower the cost of prevention of the flooding for the government. And last but not least, we will increase, most important, the resource management to save people's life, to buy time for the people to save their properties for their lives. So we have the flood level data and the rainfall data. They're all real-time time series data. As a data scientist, maybe some of you are, what's the first thing coming into your mind? Probably you do a linear regression, right? This is what I was trained in doing data science, easy. But does this really look like that? Or probably you do a REMA because it's a time series data. So the question we asked ourselves is, I'm going to show you the question. How hard could it be, actually? Right. So I'm going to hand this over to Ian, who is our data scientist, expert of machine learning. So the machine learning expert, the evening of the guy of the evening, sorry. Yeah. There you go.
Do you need this? What do you get?
Yep.
Wait a second.
This is Russian. Yes, you do.
There you go. Just I believe it. This should be fine. It's coming. Nope. Oh yeah.
We can try this one.
Yeah, there we go. It's coming. There we go. Like I'm gonna have to.
You can use it if you want.
Yeah, cool. We might do. I'll keep it and I'll give it back.
I'm gonna sit here.
Yeah,
You
I'm
know,
gonna have to sit here. You start and I'm gonna just.
Okay. So basically, how hard could it be? That's the first impression I have, because I think some regression model will solve this problem. But after I did some, after we basically did some exploratory analysis, we do find it's not that easy actually. So that's basically why we are here. We want to share this experience with you, and also we want to get some feedback from you. And hopefully that some of the things, some of the methods we used, some of the model we created would be helpful for you also. And we're fixing it.
It's working for a live stream. Yeah, there.
那能不能这个换一个？它那个接口是什么？HDMI。这个有吗？
Okay, good. So before I start to talk about how to train the model and everything, blah blah blah, I would. Well, I want to first do a quick recap. So basically, to show you what kind of data we have. And you already mentioned some of them. The flood data is the first data we have. The flood data basically is collected by the flood stations. So the flood station has a IoT sensor. Basically, it keeps monitoring, measures the flood level of their place. And the data we got, the data is reported to the server and saved in a database. The database looks basically like this. It's very simple. You have a timestamp, and you have a station ID, and you have the height. The height is the level of the flood in centimeters. And each station is continuously send this data to our server, but the time interval is not fixed. What that means basically when the flood level is high, the frequency increase. Why is that? Because when the flood level is high, we want to keep a close eye on it, because there's a high possibility they will develop a significant flood, and which probably will cause some damage. And when the flood level is like this, 0, and it's like okay, it's just okay. There will not be flood very soon. And the second data set we have is the rainfall data. The rainfall data is basically measured by the weather stations. They have rain gauges at each weather stations to basically it measures the amount of rainfall over a set period of time. In our case, it's an hour. So basically, an hourly based rainfall data is sent to sent to the server and saved in a database. The structure of the table is also very simple. It's typical time series database. We have timestamp, a station ID, and also the hourly, the volume of the hourly rainfall, which is in millimeters. And in this case, it's a little bit different from the flood data. Rainfall data, the time interval is fixed. It's hourly data. And we have the city we're walking. The city we're collecting data from, it has 146 weather stations. So the data, with regard to the data size, basically over a year we have around 1 million data points like this. Oh,
Since I moved.
you really? This is real.
There it is. Yeah,
When we switch to another laptop,
it's the connection. It's the laptop. is fine. The connection is just, yeah, it doesn't like the weight.
It's a laptop or the laptop.
Yeah, I mean we can,
Sure.
or if you, we can just put it on a flat surface and you can click through it.
Yeah, also
That's also another option, right?
maybe it's also. 有时候不是很快。
Flat service, come on.
There it is.
Yeah.
No? Nope. You keep talking. I will
Okay.
do this.
And the third data set we have is basically we have a weather station, have a rain station. For each of these stations we have its basic information, descriptive data. So basically it has various columns like location, address, and some who are maintaining these stations. Yes. Yep. This is the geo information of each stations. As you can see on the map, it's spread out throughout the city, and for each of these stations, it has a longitude and latitude. Longitude and latitude are only data we use for our analysis. So basically, these are the data sets we have. It's pretty simple and straightforward. If you have any experience with time series, especially time series data from IoT sensors, should be quite similar. Should be familiar for you. And as I said before, at the beginning I thought it was pretty easy. But after we did some exploratory analysis, we find it's not that easy. The reason is that we find some challenges, and I would like to explain briefly about the challenges. Also, we have the common issues like if you do data analysis, you all have experienced this. Common issues is data quality and unbalanced data set. Data quality, we basically mainly have two issues. First one is missing values. I've seen some flood sensors not reporting data for a few hours, sometimes even a few days. And the reason, according to our customer, is that the IoT sensors are not really trustworthy. Sometimes they just fail to work. And the extremely high values is another problem we noticed when we went through our data. But basically, we saw that some flood level is extremely high. It's like larger than 300 centimeters. We were a little bit suspicious about this. So we contacted our clients and we asked them, we confirmed with them whether this actually happened or not. And the reply we got from them is basically, this is some errors from the IoT sensors. So it's never a flood more than 300 centimeters. And so we consider these extremely high value as outliers. And the unbalanced data sets, I'm not sure how many of you are data scientists or data analysts. If you do any classification tasks, you try to build a prediction model to predict classes, you probably would experience these issues. One example is that the classical example is credit card fraud detection. You have millions of transactions, and only a very small amount of those transactions are actually suspicious and fraudulent. The vast majority of these transactions are just normal transactions. This is the unbalanced data set I'm talking about. In our case, throughout the year, only a few days, maybe even hundreds of hours, there are actually floods. The rest of the time, there's actually no flood at all. Even though there's a little bit of rain, but there's no flood at all. The flood level is very low, is around 0. So that's the unbalanced data set issue we have. And we also have a few specific issues with relate to this project. And the first one is to calculate the volume of the rainfall for each flood station. So you might be wondering why we need to calculate the volume of the rainfall for each flood station. Well, as you can see on the map, the red ones are the flood stations, the blue ones are the weather stations. Basically, in order to predict the level of flood, the future of a level flood, you basically need to know the current status, the current flood level, maybe the historical flood level, and you also need to know whether it's going to rain or not in the future. But the flood stations we can collect, flood station monitoring the current flood level and also has a historical flood level saved. There's no problem, we can get this. But for the flood station, there's no rain gauges to measure the level of rainfall. Weather station has this. So basically, we need to find a way to match these two. It's basically just a match problem. Well, the simplest way is just to pick the nearest weather station for the flood station. But when you see on the map, some of the flood station, like this one, it has a very close weather station. In this case, if you use rainfall data, rainfall information from this weather station, it's pretty accurate because it's very close, just the same place. For this case, to have weather station, nearest weather station very far away, in this case, it's pretty difficult. What we did, so basically we use a weighted, distance-based weighted rainfall calculation. Well, this won't solve the problem, the distance problem, but at least we thought it would make it a little bit better. And a specific example is that if this is the flood station, we want to get the rainfall data for this flood station, we basically pick a number of nearest weather station for it. In this case, n equals 3. So we have 3 nearest weather station for it. Then we assign weight for each of these weather stations. The closer it is between the weather station and the flood station, it is, the higher the weight it is. So basically, we calculate the rainfall, the level of rainfall for each of the flood station. The second issue we have is about the thing I already mentioned, the flood level. The time interval of generating flood level is not fixed. Sometimes it's every 5 minutes, sometimes it's every hour. In this case, if we slide the data into a fixed time window, let's say 1 hour. Why 1 hour, you might be wondering? Well, as I said, as I explained, the rainfall data is hourly based, and what we want to predict is also at an hourly level. It's all about the data granularity. So that's why we split the data into a time window, a fixed time window. This fixed time window, we choose 1 hour. If we do that, we will get a table like this. What's the problem with this? Missing values. So how we do? We need to fill in this missing value, find a way to fill in these missing values. Well, what we did is pretty simple. We just fill in with calculate the mean of the neighbors. And after we fill in these missing values, then we can move on to do feature engineering and etc. The third issue we have, and Yudi already explained that, our customer wants to predict the flood severity of the next 3 hours. So there's 2 ways to do this. The first way is that, okay, 3 hours, we cut this 3 hours as a big time window. So what would happen to the end of the 3 hours, what would happen in the big time window? And the other way to do it is like we predict what would happen each hour of the next 3 hours. And our customer do not want the first one. they want to have this second one. If we want to build regression model to predict the second formulation, the traditional regression model would not work. The traditional regression model you might familiar with like SVR, linear support vector. SVR represents support vector regression. Because for linear regression, support vector regression, you need to have a single output, not like a sequence of outputs. That's the problem. We need to find a new one. Luckily, there's one who can handle this. This is a sequence-to-sequence model. Sequence-to-sequence models basically you can take the sequence of inputs with a fixed length, and then generate the sequence of output with a fixed length. And the length of the input sequence and length of the output sequence can be different. Let's say you have a input sequence with a length of 10. The output sequence could be 1, could be 5, it could be 20. There's no problem with that. And for each of the data at a different time step is a multi-dimensional vector in our case. So basically, these are the challenges we have, and also I explained a little bit about the data we have. And now basically we can start to build the model, and it takes basically only 3 steps to build the model, and the last step is to deploy it. And I'm going to talk about each of these steps, what we did with the data. The data preprocessing is pretty simple in our case. We just remember the outlier I talked about. So basically, we replace its outlier with normal values. And also, again, we use the neighbors, mean of the neighbors. And I did a little bit of scaling. So basically, that's all the data processing we did. One of the reasons we did so little processing because our data is sort of pretty simple and not that many noises. And the other thing that we want to keep the data as clean as well. We don't want to add too much our inputs into the data. And the feature engineering, after filling in the missing values for the hourly sequence, we can calculate the features. The features, we have a number of features in our feature list. The first features are the aggregated features. Like we use these aggregated features to represent what is the average level of the flood within that hour. We also, as you can see, we use standard deviation to try to show the movement of the flood level within that hour. And also the rain, the feature of the amount of rainfall, I already explained how we did that. And also the station history. So basically, there are flood stations that are very prone to flood. Even with a little amount of rain, it will get flood there. There are also stations that have very little chance of getting flood. And so basically, we calculate a number of features to, based on the history of the flood, to represent how likely a flood station is prone to a flood. And one of the example is the count, like how many floods happened during the past. And so basically, these are the feature set we calculated. And in order to build this sequence-to-sequence model, this feature set are the input features. Wait a second. The multi-dimensional vector I'm talking about. And we also need to target sequence. Target sequence, we basically use the mean of the hourly sequence. So basically what we predict is the average flood level of that hour. So if we did for all our data set, we will get a metric something like this. These are the hourly features. These are the features that represent what the flood level, what the situation, what is the flood level during that hour. And these are the average flood level during that hour. Yep, already explained here. So basically, we are going to build a sequence-to-sequence model. We need to have our sequence. The sequence, what we need is just a slide, slide windows of T hours. And then we will get the input of a sequence on the left side. And on the right side, we will have the output of a sequence. And the output of a sequence is 3. The length of our output sequence is 3. We already know our customer wants to know the next what would happen the next 3 hours. The input sequence, the length of the input sequence is t. This t could be any number. This is something that you can choose and you can try. So basically, these are the input for our sequence-to-sequence model. With this input, we can basically start to train our model. But we did a little bit extra things. So as I have explained, we don't have a really geo information because geo information is also a good indicator of how likely a flood station, how likely a place is prone to a flood. Let's see if it's eternal, then probably with a little amount of rain, then you will have flood there. So what we did, we tried to use Google Maps API, and also there's another Maps API called Encoder. Maps API Encoder is a Chinese company providing mapping services in China. And for Google Maps API, we collect the elevation information. So basically, our assumption is that we basically collect the elevation of that flood station and also the elevation of its surroundings. Our assumption is that if the elevation of the flood station is lower than its surroundings, then this flood station probably has a higher chance of getting flood because water accumulated from the surroundings to that place. This is a lower point. And for the Google Maps API, so we get information like how many restaurants within the 1 kilometer radius, and also are there any tunnels nearby? Are there any metro stations nearby? This kind of information. And we will also use this as an input for our model. So the model we're trying to build is a sequence-sequence model I already explained. And because sequence model is a model basically has an encoder and decoder. That's why sometimes people also call it encoder-decoder model. Before I train the model, I show you how I train the model, I would basically give a brief explanation of what sequence model is. I assume that many of you, some of you might have never heard of it or never used it. So sequence model is basically a recurrent neural network for sequence prediction. Recurrent neural network. I would like to take a poll, like how many people have heard of a recurrent neural network? Okay. Number of them. Okay, that's good. And so basically recurrent neural network is, there are basically two types of neural network, mainly two types of neural network, convolutional neural network and recurrent neural network. Convolutional neural network basically doing very well in computer vision tasks, can achieve amazing results in like image classification. And but this kind of feed-forward neural network has a problem. It cannot process information that has a time and order elements in it. So that's why recurrent neural researchers created this recurrent neural network. Recurrent neural network basically can take in, can process information that has time and order to it. Recurrent neural network, as I show in the left side, is just a neural network with loop in themselves. If you unroll these loops, you will get a chain-like structure, like on the right side. And why they created recurrent neural network already explained. The example input of recurrent neural network could be like this. Could be sentences, and it could be a numeric data with times like a Bitcoin price. The sequence model, the overview of a sequence model is like this. It has an encoder and decoder. It works like this. In this case, we have sentences in English. encoder take this sentence as input and transform this sentence, this input sentence into a basically. People sometimes call it as a hidden state. Sometimes people call it as context. This is we just call it as hidden states here. Hidden states is from encoder, and this hidden state is passed on to decoder, and decoder take this hidden state as an input and generate the target sequence, which is a sentence in French. This is basically an overview of the sequence model. The use case of sequence model neuron, the most well-known, I think, is the neural machine translation. I think Google Translation also use this. They have a very sophisticated model. Also, chatbox, Alexa, I think they also use this auto reply, and also time series they can use this. And as I showed before, both the encoder and decoder are basically just a recurrent neural network. For recurrent neural network, you can unroll it. If we unroll it, that we get a chain-like structure for both encoder and decoder. So the decoder, you can see that it's taking the sequence of words, the order in its original order, one by one, and get here. Here calls it named as internal state. This is the same hidden state, and the hidden state is passed on to the decoder, and decoder takes in this hidden state and start to generate the target sequence one by one. So basically, this is how sequence model works, and there are three options for each of these recurrent neuron units or neurons. Each of the units, there are three types of. You can choose from one of these three. The first one is the vanilla recurrent neural network, just the default one with no special settings. And the other one is long-short LSTM, long-short-term memory. And the third one is GRU, gated recurrent unit. And about gated recurrent unit is just a variant of, can be considered as a variant of LSTM. And here I'm not going to explain what GRU is, because we are not building a GRU-based sequence model. We are building a LSTM-based sequence model. So LSTM, the internal architecture of LSTM is like this. It can have 4 neurons inside each unit, and each of these units play a special role in. And why we have LSTM? Why LSTM is created? So basically, as I explained before, recurrent neural network can take in a sequence, information with order or time. But when the sequence gets longer and longer, here we have a very short sentences. Imagine if it's a paper. Imagine if it's a paragraph with 200 words. In this case, default one, vanilla INA, cannot handle this. Information will get lost. They cannot pass the correct information to the decoder. And that's why LSTM is created. LSTM actually can handle this long-term dependency. I'm not going to explain the detail each of these neurons, so I don't have a lot of time. And if you want to talk about it, we can discuss this afterwards. And also, as I showed this, this is a single layer sequence model. Of course, you can build a multiple layer and make it as complicated as you want. Let's back to our prediction task. And we wonder, we have everything. We can start to build model. No, not yet. The last thing we need to do before we train our model is need to define our performance metrics. Why we need to do this? Well, it's very simple. Because we are not going to build one model. We're going to build a couple of models. How do we know which one is better? So we need a performance metrics to measure that. And to define your performance metrics, you basically need to match your prediction goal with the performance metrics. What is the goal for this project? Specifically, it is that the higher the flood level, the more crucial to predict it correctly. This is easy to understand, right? Because the higher the flood level, there's a higher danger that could get a significant flood, which could cost a lot of money or cost lives. So we need to really predict that correctly. And for the flood level that is around, yes?
I have a question.
Yeah, sure.
As I understand, you have two types of sensors: flood level and rainfall.
Yeah, yeah.
And which data you use as an input parameters?
Input mainly from the flood data.
Only flood.
Yeah, not only flood data, we also combine the flood data with the rainfall data.
Okay, so
Yeah, it's combined, but it's based on the flood data.
And which data you use for like teaching the model?
Teaching the model is flood data,
Flood data.
but with rainfall information.
Okay.
Yeah. Yeah. So with regard to the flood level, that is around 0. So if we do not predict very correctly, let's say if the flood level is 5, we predict it as 0. Really not a big issue. They won't do anything at that flood level anyway. So basically, the customized metrics, performance metrics we developed is like this. This is the mathematical formula of it. So basically, it's a bit like the weighted classification classification model. So if the formula is not, I have a specific example for this. So basically, on the left side we have the true values. On the right side we have the predicted values. Based on this, we can calculate the errors, absolute errors, like this. If we use the normal performance measure, the predefined performance like MAE, mean absolute error, or mean squared error, you basically sum up all the errors and divide it by the amount of values in the table. But with our customized performance metrics, we need to first check which errors we want to take into our calculation. So basically, let's see, we want to only calculate the flood level that is above 10. In this case, we have 8 values selected, and when we calculate the errors, we only take these 8 values into account. Then we will get MAE 10 as this 26.8 is the sum of these 8 absolute errors, and the count, the number of values we take into account is 8. So we got MAE 10 3.38, and MAE 20 is 2.16. Then we have our performance metrics. Here I use the error metric, basically the same thing. And the loss function we use the mean squared error, just a normal one. Mean squared error is appropriate for regression issues. And then we can build the model. Yeah, we use Keras and TensorFlow. How many of you have experience with TensorFlow? Okay, nice. Keras? Okay, nice. We basically, there are tons of resources available. I think it's pretty easy to start. The model we built, well, when you build the models, you first want to have a baseline, quickly build a baseline. The baseline, we did that. We have a baseline. This baseline model is just the default, all the default sequence-to-sequence model. We didn't add anything, we didn't remove anything, just the same. This FC layer, the previous diagram, the sequence diagram, you don't see this FC layer, but this FC layer is always there. The previous one just did not include it. But this FC layer is not, we added. FC layer is basically fully connected dense, further connected to the layer. This is the baseline model. For the second model, we basically incorporated the weather forecast information. As I said before, in order to predict the future flood level, you need to know current flood level, historic flood level. You also need to know whether it's going to rain, how much it's going to rain in the future. That's why we added this into our model, and we added at the decode layer. So before we put the output of the LSTM model through the FC layer, we concatenate them together and put it together as an input. Then we get the target value. And the third model, also the last model we built, is we incorporated the enriched data we got. So basically, the enriched data is added from the encoder layer. Before we added this data to the LSTM model, we basically add a FC layer. FC layer, basically, we want to do a little bit dimensionality reduction. And so basically, these are three models. Let's see the results. The results, we have two customized performance metrics. This one is the predefined. It's rooted mean square error. I added here just want to show you, if we don't use our customized model, then what would happen? How can we pick our model? As you can see, the rooted mean square errors is very low. It's very low. If we evaluate our model based on this, we would see we have a really perfect model. And also another problem is that the difference between these three models is basically the same. It's not a very significant difference. But if we took a look at our customized metrics, it sort of make more sense. Let's see, like the MAE 10. So basically, you can see the error range is 3.3. For the third one, give the best results. What this means? This means if the let's see, the true value is 15. What the range of our prediction? Our prediction would be, let's see, 12 and 18, around 12, 18. But for our clients, 12, 18, and 15, it's basically the same for them. So they are this is the acceptable error range for them. But for the MAE 20, the results is even better. If the flood, let's say if the flood level is 25, what we would get? We would get 22 or 28. In that case, it's also sort of the same for them, because if it's 25, they need to do something. If it's 22, they also need to do something, because the chances of getting a flood are quite the same. And these are the results of the three models, and the third model basically is the model we choose. But I would like to point out the second model and the third model, basically, the difference between them is not very significant. Probably the re-enriched data process is not necessary. And a little bit more about the model. The T, as I said before, explained before, T is something that you can choose, and the T we use to build our model is 12. So basically it means we use 12 hours of historical data to predict the next 3 hours. And we also try another number. We tried a 10 and we tried a 5, and this 12 gave us a better result. And the hyperparameters about the model is that we use the Atom as our optimizer. The epoch size is 50. And about the deployment, a few words about deployment is that the model we deployed is the third one. And we are also regularly retrain the model because new data are collected, new data become historical data, then we feed this into our data and to retrain it. This is the dashboard dashboard that shows the results of a model, of our prediction. So basically, that's the model. I think Yuli has a few words to add, okay, or not?
So I think I'm going to wrap up, because it's not a good time in the summer to organize this kind of meetup, because our data engineer is on vacation, so it's not here. So I'm not going to talk too much about the data pipeline things we built, but what I can tell you is this is the thing that he gave me. we don't have Kafka or sensors directly connect to the database we have to our cloud. What we have is actually the external data source, because they are using the Oracle database and they push the data directly to our database. So maybe next time another meetup to talk about the data pipeline that he built. So unfortunately today I'm going to kind of skip this, and if you are interested can reach out to us and we can explain more, because this is actually very important when you really deploy the model, because you're going to automate all the processes, include the model retraining part. So I'm going to wrap up very quickly. So the results is the model we deployed can actually predict the flood level in 3 hours in advance with a high reliability. So what Ian just explained, the MAE 10 and 20. So the action that the government is now doing is they're testing our prediction model against their expert experience. You know, those people who point out on the map, this is a dangerous area, that is dangerous area. So. And the benefits that we believe, once in production, now it says they're still in pilot, so they are testing if it's the accuracy is really that high or it's just a lie from us. So if it's in production, we believe the city will have better flood prevention and rescue system that will be embedded into their existing system, and that will save millions, not just for the operation or resource management of the government, but also for the civilians living in the city to prevent the loss of their properties during these kind of disasters. I think that's pretty much about the presentation. Please shoot your question. So,
Yes. Yeah, please.
I was just wondering, you were looking for these 3 predictions, right? 1 hour, 2 hours, 3 hours.
Yeah.
And you showed that if you were only asking for one number, you could think about using linear regression or SVR.
Yeah.
If you only needed that one number, would you have chosen an RNN or a sequence model, or would a linear regression have worked just as well?
The one number is not enough for us.
You haven't tried that either. No, because as a baseline, right?
As a baseline, probably it would work, but what do you mean by predicting 1 hour? 1 hour, in that case, we would have...
you would have the 3 hour prediction as a one number.
Yeah. We can try that as a baseline, but I think our customer would not be very happy with it, because if we tell them, okay, within the next 3 hours, something would happen, but they start wondering, which hour of these 3 hours?
Yeah, okay, but I'd be interested to see the
as a
3 hour
baseline.
prediction, how it would be different from your sequence to sequence
Oh
model, right?
Yeah. I think that would be an interesting comparison, but I think that would be an interesting comparison. Let's put it that way. Yeah.
Because that would be a much simpler solution, and you could maybe have 3 linear regressions, one for every hour or whatever. But okay.
Yeah. I think it would be interesting comparison as a baseline.
Yeah. Okay.
Yeah.
If you go back to the table with errors, you can see that the errors for predictions without weather forecast is almost the same as with.
Yeah.
Why
I don't know. I'm a little bit. Let's say I thought the enriched data would be very helpful, but the results shows it's not that helpful. My explanation, possible explanation would be the enrichment. We did not get the enough data, or did not get the correct data, because we pick these variables like what we want to enrich, like how many restaurants and how many metro stations. This we pick randomly. We did not have the experts to help us, like geoscience, people who know geology, who can help us provide this input for us. We do this by randomly pick some variables.
What did you use for the input for the weather forecast?
For the weather forecast, we as I said before, it is also from the weather station. The weather station, they not only measure the past, like what is the amount of the rainfall in this hour. They also collect weather-related variables like wind and etc. They use their prediction model to predict what is the amount of rain we are expecting in the next hour, in the next 2 hours.
What did you use? Which parameter did you use for your model?
For the model is the amount of the rainfall. The amount of rainfall. Yeah, the amount of rainfall. Yeah.
Just to add to the second question, the reason that the enrichment data is not helping improve the model a lot is because the map API we're using probably it's outdated because developed very fast in the city. So the restaurant there last month probably it's become another shop. That's why we cannot really validate how accuracy the map API data is. That's why probably this doesn't show a significant difference for this enrichment data. Sorry.
Yeah, so you didn't use data from weather forecast like satellite imagery or something like that? More on a larger level?
No, we first of all, I'm not sure whether we have access to this kind of data. Are these data public available?
In the Netherlands.
In Netherlands from Google Maps?
No, it's another provider, but yeah.
Oh, and AccuWeather, right?
Sorry?
AccuWeather.
You will get them 3 days after the acquisition.
No, but something like BioAlarm in the Netherlands. It's actually it's a radar that detects.
Okay.
BioRadar is different.
Yeah, but it's actually it's not 100% accurate, but it's very interesting in these kinds of scenarios.
Yeah, but first of all, I'm not sure whether this kind of data are public available in China.
Okay.
And second of all, because we already have the weather forecast data, the weather forecast is kind of taking into this account.
Yeah, but it's maybe not as accurate as.
Yeah. Okay. Any other questions? Yeah.
I think the feature engineering is very important for this project. Do you consider about, because this is a time series data set, do you consider about to do something like remove the stationary, remove the seasonality in the feature engineering phase?
I'm not sure about seasonality. In the summertime. Yeah, that's something that we can. Something we can improve a little bit, the seasonality, because in the summertime there's more typhoon, more hurricanes, and it's more likely that flooding to happen during this kind of time. Yeah, I think that's a good point.
When I did that, sometimes I give quite a lot of improvements.
Okay. Yeah, I think it's a good point, and it's something that we can try.
Second one is that also related to the baseline model. Do you even consider compare with the, for instance, the resistant model? Let's say now we get data at 7 o'clock. We just assume the 8 o'clock, 9 o'clock, 10 o'clock is exactly the same as 7 o'clock, and we calculate this RMSE and compare to your model.
What do you mean? I'm not sure. I got your question.
For me, when I developing time series model, I always compare first one to build a baseline model.
Yeah.
So this baseline model can be very simple, something like looks like no useful. For instance, now 8 o'clock the rainfall is 12. Then we think 8 o'clock is also 12. 9 o'clock is also 12. 10 o'clock is also 12.
Yeah.
Then we also calculate this kind of matrix and compare with your model.
Okay, that's something I'm not sure we can do that. Let's see. You mean like here? We can do something here, right?
Here you are defined the matrix.
Yeah.
On the amount of.
Yeah. But we are not really predicting one by one. We basically get a sequence, directly get a sequence out there. Sequence with 3 values out. It's not one by one.
I will discuss it with you.
Okay, sure. I believe we have another question. Yeah? Yeah, sure.
Does your prediction get worse when, like, is your prediction in the third hour always worse than your prediction in the first hour? This might be a very stupid question, by the way.
No, we don't really have this kind of this comparison like the 3 hours and the first hour. We don't have we only predict 3 hours. The output is always 3 hours. A sequence with 3 values. We don't have like a.
Yeah, but
Sorry?
Do you measure the stochastic use of
No, we don't really measure the accuracy. We just have the error range. The error range is basically how we measure our performance. Yeah.
Do you correct, like live correction of prediction, for example, prediction? You predicted like some level, and then after 1 hour you see that that data is not like it's higher or lower. Do you correct prediction like live correction?
We don't. We don't really correct the predictions, but we do like for example, if at this moment is let's say 8 o'clock, we predict 9, 10, 11. Then at 10 o'clock we predict 10, 11, 12.
So it's like really time windows.
Yeah, time windows. Yeah. Any other questions? Okay, that's nice. I think one last thing I want to add is like I'm doing a PhD at Utrecht, and my research is mainly how to analyze medical data. If you have any medical data you want to collaborate with me, I mean just for research. I mean you can you can contact me, you can discuss with me. I mean for my paper and for your project. Yeah, thanks.
Okay, yeah, thank you so much for doing that presentation. It was really interesting and quite technical. If any of you want to watch that back, if you missed an equation or want to try and replicate something like it, we streamed it on YouTube and hopefully it recorded perfectly, so that's great. Yes, you should be able to watch it back. I'll send the link out in the email after this. The pizza, I'm hoping, is on its way, because otherwise we will starve. So it should be here any minute now. I need to prep the raffle, so it'll take a couple of minutes because I need to do a few things. If everyone could stack the chairs on that side, and then hopefully there's a few beers. If there's not, I will fix those first. And if the pizza turns up while I'm prepping, the pizza comes first. And then I'll try and get your attention a bit later. And we'll do the raffle. Thank you. Sorry about the technical issues we had in the beginning.
I thought it's something wrong with my laptop. It's not.
I think it's the dongle. Like the dongle doesn't like not being supported.
It could be because I rarely use it.
Yeah, it's super annoying. Yeah, but thankfully when you put it on a flat surface, it works really nicely. So.